All right, so I'm going to finish these notes for you. Geosynchronous means that it is the same period as the orbit of the Earth. So we already know that T is going to be equal to what, 24 hours? But we don't need that in hours. We actually need this in seconds. So there are, 60 minutes in 1 hour. Sorry. We got 60 minutes. And in 1 minute, we have 60 seconds. So 24 hours, if we multiply that together, we get 86,400 seconds. Here's your trivia for the day. All right, so we have the period. Now, what we did know is that it wanted us to find the radius and the speed of the geosynchronous orbit. Okay, so we know how to relate some of these things. So what do we know? Well, first thing we know is that the velocity is equal to what? 2 pi r divided by the period. Okay, so I got that one, but I don't know r. So maybe I need to start with r first. How am I going to find r? Well, I got a formula right up here, don't I? What do I know? I know that 4 pi r cubed is equal to gmt squared. Correct? Okay. So let's plug all this in and solve. So r cubed is going to equal gmt squared over 4 pi squared. 4 pi squared. So let's plug in. 6.67 times 10 to the negative 11. M is the mass of the Earth, which is 5.98 times 10 to the 24th. Period we found was 86,400 seconds. That's going to be squared. We're going to divide that by 4 pi squared. And the last thing we need to do is get rid of this cubed. So we're going to take the cube root of everything. So we're going to take the cube root here. We're going to end up taking the cube root of this whole thing. What you should end up with is an r that is approximately 42 million meters up in the air, thereabouts. Okay, so now we know r. That's just math, work through it. So now if we know r, we can plug it in over here along with our period. So we get v 2 times pi times that radius of 42 million divided by the 86,400 seconds that we had from before. And what we end up is getting a velocity of about 3,070 meters per second. Just work the math. Remember, what is our relationship here? This is my relationship. T squared GM equals 4 pi squared R cubed. All right. Kepler's third law as a short sentence and as a ratio equation. What we know is that for all objects, orbiting the same center, our ratio of t squared over r cubed is constant. Okay? Now, derivation of Kepler's third law, we've done this once already. We know that gm over r squared has to be equal to little m v squared over r. So little m goes away, and one of the r's goes away. So we are left with gm over r equals v squared. Well, we know what v squared is. V is equal to what? 2 pi r over the period. So if we square both of those, we get v squared is equal to 4 pi squared r squared over t squared, which we are now going to take and put there. So if I take this over to the side over here, because I want you to see it, we now know that what g, well, maybe I'll put it, yeah, I'll put it over here. Big GM over r is equal to 4 pi r squared over t squared. I'm now going to cross multiply and take the t squared over here and the r over there. So I'm left with GM t squared equals, that should be a squared, 4 pi squared r cubed. Okay? So there's my Kepler's law. Now it said it's constant, so how do we know it's constant? Well, guys, if we look at this and we put r squared or r cubed over t squared, then I'm just going to divide both sides by t squared. That goes away, and divide both sides by 4 pi squared. And I want you to look. R cubed over t squared is equal to big G, which is a constant, m, which is a constant, over 4 pi squared, which is a constant. So this is Kepler's law, and that is constant right here. Okay? So let's finish this up. It says, test your understanding. Suppose you know the moon orbits the earth with a radius, so we've got a radius right here. Takes 27.3 days to go around the earth. Okay, so there's my period. 27.3 days. Geosynchronous satellite takes 1 day to go around the earth. What is the radius of a geosynchronous satellite? So what do we know? We know that the period, Kepler's law, has to be constant, doesn't it? So we know that r cubed, excuse me, doing this upside down, we know that r cubed over t squared for the satellite has to be equal to the same r cubed over t squared for the moon. Sorry, moon. Okay. So what we know is the period of the, or the ratio of the satellite. If we do this, cross multiply some stuff, we get r of the satellite cubed is going to be equal to r cubed of the moon. Satellite squared over moon squared. Okay, radius of the satellite, or the moon, is 3.84 times 10 to the 8th. We're going to cube that. Multiply by the period of the satellite. Well, the period of the satellite is 27.3 days. So we can just do 20.7.3 squared. And the period for the moon is, nope, put that in the wrong place. Satellite is 1 day, it's geosynchronous. So that is 1 day, and this is 27.3 days squared. So if we do this, then we can figure out I'm going to have to erase here, guys. We get approximately 42 million meters, which is what we got before when we found the geosynchronous orbit. And yes, there is only one geosynchronous orbit for each planet. That's why we have to be so careful and restrictive of what we put up in outer space, because that orbit gets kind of crowded. All right, so Earth's distance from the sun is defined as 1 astronomical unit, okay? And Earth takes 1 year to go around the sun. So 1 year around the sun, so that's the period of the Earth. Saturn is 9 astronomical units from the sun. So this is the radius. How long does Saturn take? This is the radius for Saturn. I hope you see where I'm going with this. We know that the radius of Earth cubed, since these are both around the same body, which is the sun, radius of the Earth cubed over the period of the Earth squared has to be equal to the radius of Saturn cubed over the period of Saturn squared. So we are looking for how long does Saturn take. So we're looking for the period of Saturn. So if I cross multiply this way, I get T sub s squared r Earth cubed equals r Saturn cubed T sub Earth squared. Now I'm going to divide both sides by the radius of the Earth cubed. And that goes away, and now we can plug in. Radius of this ends up equaling to what? Saturn is 9, so we take 9 cubed. Period of the Earth is 1 year. Radius of the Earth is 1 unit cubed. So what we know is that this is equal to period of Saturn squared is equal to 9 cubed. Now I'm going to be easy on myself and take the square root of both of these, which means that this is period of Saturn is equal to the square root of 9, and then I can cube it. Square root of 9 is 3. 3 cubed is 27. So it is 27 years. 27 years. But you see how handy that Kepler's law relationship is. That they are constant. Okay? Now, last one. Suppose you have data for the period of the orbits of 5 of Jupiter's moons. You also know that the radius of each of the moons. Correct? What data should be plotted to give a straight line fit to the data? Well, we know that it's what? We know the relationship is t squared to r cubed, right? So pick one. If the horizontal variable is t squared or r cubed, because we're doing what? Radius versus period? Yeah, we're going to measure the radius and do versus period. So the radius would be r cubed because of that. That would make the vertical t squared because of that. And now we're going to actually figure out what the slope is. Well, we know what the equation is. The equation of the line is what? T squared times what? What did we figure out? Well, we found from the previous page. So t squared gm equals 4 pi squared r cubed. So if this is my y and this is my x, then I need to get my y by itself. So I am now going to divide by gm and divide by gm. That goes away. If I compare that to y equals the slope times x, if x is my r cubed and y is my t squared, then guess what the slope is? Slope is 4 pi squared over gm. Okay, so we can even linearize orbit information. Okay, so now it says objects in orbit appear weightless. That's because these guys, and not because there's zero gravity, because you know now there isn't zero gravity. This is that idea of falling away. The Earth is falling away from you the same rate you're falling towards it. Okay? And everything falls together. And in other words, the ship along with you, you don't ever move towards the bottom. You never move towards the wall or the floor or anything else. So what ends up happening is you seem to float. You appear to float. So you never reach the floor of the ship. You appear to float, okay? So that's really what's going on, okay? It's falling away from you as you're falling towards the earth, and since all of it falls together the same amount, since you're all in the same orbit together, then if you push off the wall, then you continue to fall the same, and the ship's continuing to fall at the same time as you. And so you float out there and just out in the middle. And that's why you have to actually push off of something to be able to move. You have to interact with that, all that stuff that's falling with you before you make a change. Okay? That's it.